Today we're going to take a look at section 1.1, which is mathematics and problem solving. Our first chapter is actually sections chapter 1 and 2 that we'll put all on the test together because this chapter 1 actually only has 2 sections. So the first one is about problem solving, and we're first going to take a look at a 4-step problem solving method. These are not necessarily concrete. We're going to write them down on every problem, but they are what you do when you work through problems, whether you do it physically by writing it or just mentally by thinking through it. The first step is to understand the problem. And so these are some things that you might actually think about when you're trying to understand the problem. Could the problem be stated differently? Is there another wording? What do I need to find in the problem? What are the unknown quantities? What information do they give me? What information is maybe missing or not needed? After you've sort of established what it is that you're being asked to find, you got to figure out how you're going to find that information. This is a non-exhaustive list of possibilities, which means that there's other options I could write down, but these are a lot of the problem-solving strategies that we're going to encounter. One of them is to look for a pattern. The entire section 1.2 of this textbook is all about patterns. Okay, so we're going to think about patterns in that section. Maybe to examine related problems. You've done that before. I know you have, because that's what happens when you look back in there, in the examples that they do to try and see if one is close enough to you, right? Is it like the one I did before? Or is it like the one she presented in class? Examine a simpler or a special case. Sometimes a problem will ask you to consider what happens when there's 10 people doing something. Well, that might be a complicated question, but if you can ask yourself, how would I answer the question if there were only 2 people involved or 3 people involved? That might lead you along the right path to deciding what you do for your 10 people. Tables and lists. Who are my list makers? Who does to-do lists? I'm a list maker, and I'm a little bit feeling out of sorts because I left my planner at home today. I've got a mental note of what's in there, but I like those lists, and I really like to mark things off. Does anybody write things down after you do it just so you can mark it off? I do that too. So sometimes it's really helpful to organize information that you're given in a list or a chart. So we'll see an example of that. A few more. Identify a subgoal. If you can sort of break it down into pieces, if I can get to here, then I know how to finish the problem. So then I can only think about like this one little bit right here. How do I get to this midpoint? Diagrams. Who are my artists? Any of you draw well? I'm not going to make you draw, so you can feel free to raise your hand. None of you. A little bit? A couple of you? Okay. So I won't grade your drawings by like your artistic endeavors. I might, because the 2 of you are like amazing, but for everybody else I won't. Sometimes it's helpful just to get a picture of what's going on. So if they're talking about cows in the problem, I might make a stick figure that sort of is my image of what a cow is, right? So a lot of the problems that we do in this section of problem solving are going to be sort of geared at a minimal amount of advanced mathematical thinking. Because remember, I told you at the beginning that this class is designed for the younger grades. So we're not going to use a lot of equations. We're not going to use a lot of X's and Y's. Not because those aren't valid ways for solving problems, but because sometimes there's a simpler approach that a 3-year-old, not a 3-year-old, but maybe a 3rd grader, that's what I meant to say, a 3rd grader could do. But they're probably not doing X's and Y's, right? So we're going to sort of gear at the non-equation approach. Guess and check is not cheating. We're going to look at guess and check. It's a valid way to think about things, especially if you have no other option of how to start. Like, what should I do? Well, maybe it's try to guess and check and see what happens. How close am I to getting the right answer if I'm guessing and then checking to see if that actually makes sense or works. Working backwards. I know you've done this one before as well. If you've ever flipped to the back of the book and said, oh, the answer is 23, how did they get that? Right? And you try to work backwards into how they could have got 23, and then maybe you can make sense of it forwards, hopefully, after doing that. So working backwards. And then I did write an equation. I did write that on the list. We don't have to have any equations for the ones that we're using. There's one very simple sort of arithmetic thing that we're going to do. It's simple in the terms of it doesn't use variables, okay? So it's technically an equation, but I'm thinking more along the lines of when we are talking about equations with unknowns, like X's and Y's, and trying to solve for things and where lines cross and stuff like that. Those are valid things to do. We're not going to do a lot with them in this class, but it is a problem-solving strategy. After you've decided what problem-solving strategy you want to try, you have to try it. So that's carrying out the plan. Implementing the strategy, performing any needed calculations or computations. Being careful to be aware of the language that's used, the mathematics that's being asked for. Checking your steps along the way, either formally, like double check that your calculator gave you the right answer by doing it a couple of times, or do it by hand and then check with your calculator, or intuitively. Does that make sense? I always talk about a class that I used to teach when I was a grad student, and there was always this question on the test that was about termites. It was a systems of equation thing, and they had to use X's and Y's, and it was an algebra course and so forth. But the point of the story is that whenever somebody told you at the end that there were 72.3 termites, you had to sort of pause and say, we can't have 0.3 of a termite, right? So checking to make sure that what you're getting makes sense to the problem. And then keeping an accurate record of all your work. I had one of my children had a teacher once, and they gave worksheets and they never checked their work, and it just drove me batty, because if he got it wrong, he had absolutely no way to find where the work was, because he was not a very structured worker, because it wasn't required of him. And so we were constantly going back and looking for things that he didn't do it linearly, right? So if you keep track of what you've done and you make a mistake, it's a lot easier to find it later. And then check your work. There's two things about checking your work. I've already mentioned them as we talked before. Deciding if your answer is reasonable. Does it make sense, right? If you find out that the number of children that this family had is 52, you might stop and say, wait a minute, did I make a mistake? That's a lot of kids, right? But then also checking the accuracy, right? Did I actually do all the steps correctly? Go back and take a once-over look through it and make sure that nothing sort of red flags you as being, oh, it said 5 plus 3 and I did 5 times 3, right? Those things happen. So we're going to do at least one of these problems today. We're going to look at Gauss. Gauss is actually a famous mathematician. It's not Gauss. It's actually Gauss. And Gauss was a very bright child. One of these days, you guys are going to have one of these children in your classroom, and you're going to be like, what do I do? This is my little Gauss. I don't know what to do with this child. So when he was in his early grade school, his teacher gave him an assignment that was intended to take the kids a lot of time. I'm sure you would never do that as a teacher, would you? Just try to buy yourself a little time. So she told them what she wanted them to do was add up all the numbers from 1 to 100. So she's thinking they're going to do 1 plus 2, and then add that to 3, and then add that to 4, all the way up to 100. And would you agree with me that that would be a lengthy process if a child did it like that? It would. And so this is what the teacher is intending. Unfortunately, or maybe fortunately so that we can examine what he did, oh my goodness, what did I do? Okay, well, we're back online. He found the answer almost immediately. Okay, so yes, I understand he's a bright child, so not all the children in the class would do this. But he actually did it by looking for patterns. So we're going to talk a little bit about patterns today. We'll talk a lot more about patterns in section 1.2. So what I'd like for you to do is I'd like for you to write down the numbers from 1 to 100, but we're just going to put a dot, dot, dot in the middle to represent some of them that are missing. So we're going to put down 1, 2, and 3. And then we're going to do that dot, 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 and then we're going to write the last 3 numbers, which would be 98, 99, and 100. Okay? And we're going to recognize a pattern. I'm going to show you what the pattern is, and then I'm going to show you a nicer way to sort of work with it. Notice what happens if I were to add together the numbers 1 and 100. What would I get? 101. And the numbers 2 and 99. 101. And if I did 3 and 98, what would I get? 101. And this can happen as long as I keep working my way inward all the time. And they're all 101s, right? So it's an easier, oops, I didn't mean to do that. It's an easier way to do this to actually write them like we're adding them by just writing them underneath. So here's my 100. Here's the 99. Here's the 98. And I'm going to do the same thing, sort of like working my way down with the 3, 2, and 1. And we agreed that they all add up to 101. So if I were to add this together, I would have 101, 101. I'd have a whole bunch of 101s. Now Now, that's not exactly the same amount I started with. How is it different than what I started with? It's double, right? I've added the numbers that I started with to themselves in a different order. But this is double what I started with. So this is the extent of my equation for today. I'm going to call this first quantity S just for sum. And that means that this is twice S, or it's double. Okay, double what I started with. Okay, I mean, we could do that. We can add 101 together a bunch of times, but it would be helpful to know how many times, right? Does anybody know how many times I do it? Erica? Well, the way it's written first. I know what you're thinking of, but the way it's written first, it would be 100. Right now, there are 100 of these over here. So why are there 100? I'll call them terms. Why are there 100 101s? Because there's 100 numbers from 1 to 100, right? What if I had started, oh, I'll do that in problem in a minute. So yeah, there's 100 numbers, all right? Now, somewhere along the lines of second grade is where it's usually taught now, a child learns that to repeatedly add together something a whole bunch of times is a lot easier if you use multiplication, okay? Second grade, third grade's where you hit multiplication these days. So instead of adding 101 together 100 times, it would be a lot easier to simply multiply 101 times 100. Now, that's still twice as many as I needed, right? So what would I have to do to get the number I actually wanted? I would take that amount and I would divide it by 2. It's twice what I started with because I added it to itself. So if I divide by 2, I can remove that double counting that I just did. So if somebody has a calculator, grab it and take 100 times 101 and divide by 2. What will you get? Does anybody have one today? Nobody has a calculator today?
20,000.
I think you multiplied by 2. Can you double check for me?
5,000.
Yeah, that's what it is. Okay. Who wants to be my calculator person for when we do have one? Because I have one calculator. Erica? Okay. All right, so yes, it's 5,050 is correct. So Gauss saw a pattern, and he saw a way of handling it in a way that was more, well, it was quicker. I mean, basically, right? It was just easier to work with. It was easier to do. And the answer is 5,050. So we're going to take that idea, and we're going to sort of stretch it just a little bit to this one. This isn't the numbers 1 to 100. It starts at 36, and it goes to 147. But it's a similar kind of problem. Agreed? I'm still adding a bunch of things together. Now, what I suggested we do in the last one is that I looked at the pairings of the numbers, and I noticed that if I sort of paired them up, the sums end up the same. Do they here as well? What do they end up being? 183? Is that right? Okay, 183. So I'm going to write them down in reverse order. It's 147, 146, 145. And then I end up with 37 and 36. And it's a bunch of 183s. Now, the question at this point, well, first I should say that of course we recognize this is double what we started with because I added all the values in twice in order to do the pairing. Now, you might be just thinking, well, why don't you just find how many terms you have and divide by 2? You can do that. The problem is, what happens if there's an odd number of terms? It feels very odd to say add something together 47.5 times. Do you see what I'm saying? I mean, there's not 47.5 terms. That's not right. There's not a fractional number of terms. So it's just a little bit easier to think about it as I've just doubled the number of terms that I have. Okay. So the question is then, how do we figure out how many terms we do have? Okay, so Erica's suggestion is to take 147 minus 36. What do you think? She's super close. Think with me for a moment. If I had all of the numbers from 1 up to 147, how many numbers would I have? I'd have 147, right? Yeah. How many do I actually have that are missing? Do I have 36 missing? I actually have only 35 missing. The first 35 are not on my list, right? Everything that would have come before is sort of missing. It's not here. And it's the numbers from 1 up to 35. So there's actually only 35 numbers that are missing. So instead of subtracting 36, we can subtract 35 for the missing numbers. So what is 147 minus 35? 112. That's how many terms we have. So there are 112 terms. All right, so again, using a little bit more advanced mathematics than addition, we move into multiplication. It's a lot easier to multiply 183 by 112 than it is to add it that many times together. And then I will have to, whether now or whether in a moment, divide by 2 because I have to remove the fact that I doubled everything. I added everything to itself. So what is 183 times 112 and then divide by 2?
10,248.
All right, let me make one comment about a caveat and then I know we're at time and I'll let you go. The other caveat to this that you'll see in your homework is that sometimes they don't always increase by 1. Let's say you had every other number. Let's just use an easy one from 1 to 100. If you went from 1 to 100 but you had only the evens, which means you really started at 2 to 100, how many numbers would you have? 50, because you'd have only the even ones, right? What happens if you had every third number? How would you figure out how many numbers you had? You divide by 3, you know, some of the numbers are missing. So there is an example of that that happens in your homework as well.